In this video, I'm going to take you through two examples of geometric proofs using vectors. So in this first situation, we have a triangle, and we want to prove that the line from the midpoint of one side of the triangle to the midpoint of the second side of the triangle is parallel to and half as long as the third side. So I've drawn a triangle here. I've got triangle OAB. So I'm going to let M be the midpoint of side OA and N be the midpoint of side AB, and as I've got in my diagram here. I'm going to show by saying that I've got, let's set some vectors. I'm going to use this first vector OA. So I'm going to let OA be represented by vector little a, and I'm going to let the vector here OB be represented by little b. And what I want to do is prove that MN is equal to half the length of OB. So what we need to do is define this line MN. So let's define this line MN by saying to get from M to N, I'm going to have to travel half of this OA, so half of OA plus half of AB. So we can describe OA as vector A, so we've got half A plus a half of, we need to define AB, and that's going to be coming down from A to B as negative OA plus OB. So that's going to be negative vector A plus vector B. So if we expand this bracket here with the half and we simplify, we've got a half A take a half A and plus a half B, so we're left with a half B. What we notice here, because B is represented by OB, we have just defined MN as equaling a half of OB. And that's exactly what we wanted to do originally, was prove that, and that's exactly what we have proven. So we can say, hence, the line midpoints on two sides, the line from the midpoints on two sides is parallel and half the length of the third side, as we've made that proof. In our second example, we want to prove that in the trapezium OABC, where OA is represented by vector A and OC is represented by vector C, and the diagonals OB and AC intersect at M, such that A to M and M to C is split in the ratio 2:1. So what we've done to help us prove this is we've let OM, as we can see here in pink, O to M is going to be represented by some multiple of the whole line OB. And we also have line CB. I'm just going to highlight that in yellow. Now CB is going to be some multiple, so I've called it y lots of OA, because this is what defines a trapezium. One pair of opposite sides are parallel. So what we want to do is now find, our first step is to find OM and OB. So we can really define that first equivalent statement that we've made. So let's first define OM. OM is going to be travelling from O to M. So we're going to travel OA plus AM. Let's see if we can define OM. Well, that's worth A plus 2/3 of AC, because as we knew before, we have got that ratio between the diagonals OB and AC. So we know that that's equal to vector A plus 2/3 of, now let's define AC. Travelling from A to C is going to be negative A plus vector C. So we've got A, take 2/3 A, so that leaves 1/3 of vector A plus 2/3 of vector C. So we've defined OM. Let's define OB. O to B, so that full distance from vertex to vertex, is defined by going from, let's do OC plus CB. So OC plus CB. So that we can define that as vector C plus y lots of OA, because we defined that earlier in yellow. And lucky for us, we know what OA is represented by. That's just vector A. So what we've done now is we have just defined OM and OB in terms of vector A and vector C. Now that we've done that, what we can do is prove that M, that vector M, that point M divides OB in the ratio 2:1. So we're going to use the fact that we have defined OM and OB and show that OM is 2/3 of OB. So let's see that work. So let's just write that. We want to show that OM is going to be worth 2/3 of OB, which means that OM, the ratio of OM to, oops, let's just get rid of that, M to B is going to be in the ratio of 2:1. So we know from previously that OM is some multiple of OB. We called that multiple X. So let's start with that. And we're going to input the things that we know about OM from previously. OM is worth 1/3 A plus 2/3. Oops. Let's make sure we write the proper third. 1/3 of A plus 2/3 of C. And that should be equivalent to X lots of how we defined OB, which was vector C plus y lots of vector A. So what we can do here is we can simplify this a little bit more. So we've got 1/3 of A plus 2/3 of C should be equivalent to X lots of vector C plus X times Y lots of vector A. What we can do now is group our equivalents on each side. We're saying that for our vector A, 1/3 should be equivalent to X lots of Y, and for our C vectors to be equivalent, 2/3 has got to be equal to x. So lovely, x is 2/3. We can substitute this in here, and 1/3 equals 2/3 times y. So y is going to be equal to 2. Just be aware that when we're solving for y, 1/3 equals 2/3 y, so y is actually equal to 1/2, not equaling to 2. So let's actually have a look at this. So OM is equivalent to x lots of OB, which means that OM is equal to 2/3 of OB. And that's what we wanted to prove. So we can say, hence, M divides OB in the ratio 2:1 for OM to MB. And we have actually proven that OM is actually 2/3 of the OB, the ratio of 2:1. So now it's your turn to have a go at the following two questions.